Alright, we're going to try to do this real quick and with a script. Alright, a limit exists anytime there's an infinitesimal variation in x that corresponds to an infinitesimal variation in y. The variation in x we're going to call delta, and the variation in y we're going to call epsilon. And this follows from the graphic sense, but now we're actually putting it into a more traditional mathematic definition. So as you can see from the picture, you have your x value that we're trying to find the limit of, which is at a, and then you have a space delta to the right and a space delta to the left, represented by a plus delta and a minus delta. You also have the same concept from the limit value that's written as capital L, and this is done with the distance epsilon above L and the distance epsilon below L. And so for any limit that exists, these two values, delta and epsilon, have to exist. Alright, so more of the definition. This is the actual formula for the definition. The limit as x goes to some number c of f of x is going to be equal to the limit value L. And the way we write the definition we just talked about is the absolute value of x minus c, in other words that gap, has to be in between delta and 0. If it's delta, then that means that we've reached the maximum size. If it's 0, that means we're actually solving for the function value, not the limit value. So it can't be equal to 0, because that means x and c are the exact same value. The same concept exists for finding the limit value, and so f of x minus L has to be less than epsilon. It is possible for f of x and L to be the same value, therefore for both of them, for this f of x minus L to be equal to 0, and that is the definition of continuous, and we'll get more into that later. So the distance between c and x is less than delta and also greater than 0, and the distance between f of x and L is less than epsilon. Now the plus or minus is on there because we have to use absolute value bars. So remember, we're talking about a positive side and a negative side in the same equation just by using absolute values. Alright, so let's do an example. The limit as x goes to 3 of 2x plus 4 is equal to 10. And we can verify this later if you wish. But we can also verify by using our formula definitions. So 0 is less than the absolute value of x minus 3, because 3 is our value, our index value. And this has to be less than our teeny tiny value delta. At the same time, 2x plus 4 minus 10 has to be less than epsilon. Remember, epsilon is also supposed to be a teeny tiny value. But what value is delta and what value is epsilon? So let's find out. First of all, I'm going to simplify these absolute value bars to 2x minus 6. Then I'm going to factor out the 2 to x minus, so I have 2 times the absolute value of x minus 3 is less than epsilon. Divide both sides by 2, and I get x minus 3, absolute value, is less than epsilon over 2. You should notice that this now matches our delta formula. By comparison, I can now say that since both of these match, delta has to be equal to epsilon over 2. Now, why did I go through and make sure that I had x minus 3 by itself in absolute value bars? It's so that I could do the comparison between my delta part of the definition and my epsilon part of the definition. This is going to be done a lot in calculus. If I can't find an answer, just a straight epsilon equals or delta equals, then I will find another equation that I can compare it to and use that to make my final judgment. In this case, my comparison has to involve the absolute value of x minus 3. So both of my formulas need to have that to get my final answer of delta equals epsilon over 2. So why is this important? Number one, calculus is based on the idea of infinitesimals. In other words, if I get really close to something, do I get a different answer than, or can I get a different answer than if I actually equal that thing? It also leads us to the concept of having a derivative. Again, this branches off of infinitesimals. Coming off of the concept of a derivative is integrals. Okay, so this is all going to build on each other. And the further we get into calculus, you'll also see that the concept of delta and epsilon will be reused in derivations later. And also the techniques that we use in this concept will be reused later as well. One last example. This one's a little bit trickier. You may want to watch this example more than once, possibly with the sound off after you've seen it. Alright, so I've got the limit of x goes to -1 of the function x squared plus 3, and this equals 4. So here's my delta formula, and I'm simplifying it first. So it simplifies into the absolute value of x plus 1 is less than delta. Then I jump over to my epsilon definition. So my actual function is x squared plus 3, and my limit value is 4. Have to simplify it. Okay, these are always the first two steps. To x squared minus 1 absolute value. Now, what do I do at this point? I have to be able to compare my absolute value of x plus 1 to my epsilon formula. Now, if you remember from factoring in algebra and in pre-cal last year, you should be able to think of factoring x squared minus 1. And if we do factor it, you'll find that this is the difference of two squares. So I have x minus 1 as my first factor, and x plus 1 as my second factor. Sorry, using a touch screen takes a little bit longer than using a board. Still has to be in absolute values. I have not removed the absolute values yet from the problem. So I have my x plus 1 from my delta, and I have one x plus 1 in my epsilon, but I also have this little pesky x minus 1. So what do I do with that? Well, first of all, I have to realize that this x plus 1 has to be less than delta, and I'm going to pick that delta has to be less than 1. This is going back to the idea that delta has to be some kind of infinitesimal. It has to be a small number. Therefore, if I pick 1 as the largest number that delta could possibly be, then by definition, delta is still a small number, because anything less than 1 is a small number. So using this idea, that means that x plus 1 without absolute values has to be between -1 and +1. So at this point I have removed the absolute values, which means that my value of x can be anywhere between -2 and 0. Plugging this back into my absolute value of x minus 1 will give me possible answers of anywhere between 1 and 3. Now remember, I'm looking for something smaller than, so I'm going to pick 3 as my substitute for the term x minus 1. Plug this back into my epsilon definition and solve for x plus 1, the absolute value of it. Do my comparison, and I get that delta has to equal epsilon over 3. So whatever I choose as my itty-bitty, tiny epsilon value for the variation that's allowed in the y, then that has to also, that divided by 3 has to be my variation in the x. Alright, I'm sorry this video wasn't so well put together. If you're still confused on it, just holler at me in class tomorrow, and see you then.